Here, and this is the 2007 AIME 1 problem 8. Here's a view of this problem. Let p of x be a cubic polynomial. What is the largest value of k for which the polynomials q1 of x is equal to x squared plus k minus 29 x minus k and q2 of x equals 2x squared plus 2k minus 43 x plus k are both factors of p of x. Okay, so q1 of x and q2 of x are quadratics, and furthermore they are distinct quadratics, meaning that, okay, so suppose they both have two distinct roots, okay, then we're gonna have what? For p of x to be a factor, p of x must be x minus and then the product of the four distinct roots, right? But that gives us a quartic polynomial. And it says in the problem statement that p of x is cubic. So these must contain one common root and then one root that is different from each other. So let this common root be r, okay? So we have q1 of r is equal to q2 of r, which is equal to 0. This is good. Now, what's even better is now that we have this condition, we can actually eliminate the x squared term by simply multiplying this by 2, q1 of x by 2, and then simply subtracting this q2 of x. That gets rid of the x squared term. And actually I should replace these with r, right? So let me actually do that now. R. Okay, so now replacing this with r and I'm doing this. This gives us 2r squared. This becomes 2k minus 58 r, and this becomes negative 2k minus q2 of x, that's 2r squared, plus 2k minus 43 r plus k. Let's just do the subtraction now. Bye-bye. Okay, and then this becomes r, 2k minus 58 minus 2k plus 43, that becomes negative 15r, and then this becomes negative 3k, and this is equal to 0, of course. So now what we can do is actually hold on one second. 15. We can actually solve for r in terms of k, right? So bringing negative 15r over, we get 15r, from which r is equal to negative k over 5. Now what's good about this is now we have r in terms of k, right? So we can actually plug in negative k over 5 into this, into any of these polynomials to go to quadratic in terms of k, from which we can find possible values of k, and then from which we can finally extrapolate the values of k that work. So let's do that. So just plugging this into q1 of x gives us k squared by 25, good, plus k minus 29 times negative k over 5 times negative k over 5, then minus k, yep, minus k is equal to 0. Okay, I have a few things in mind. 25, let's multiply this by 5. So this gives us, multiply top and bottom by 5, this gives us plus negative 5k squared, negative 5k squared, negative 5 plus 145k, right? Just make sure I'm doing this correctly. Negative 5k squared, and then 145 plus 145k over 25, and then this becomes negative 25k over 25 is equal to 0. Good. Now we can actually multiply both sides by 25 and group like terms to get negative 4k squared plus 170. This becomes 170. No, this becomes 120k is equal to 0, right? So now this gives us negative 4k times k plus k minus 30 is equal to 0. Okay, so k is equal to 0 or k is equal to 30. 10 testing k is equal to 0 gives us what? q1 of x is equal to x squared minus 29x, and then q2 of x is equal to 0, 2x squared minus 43x. So these don't contain a common 2x, 2x. These don't contain a common root x other than x is equal to 0. And hence this solution is bogus. So let's try k is equal to 30. When k is equal to 30, we have x squared plus x minus 30. This is q1 of x. And q2 of x is equal to q2 of x is nothing but 2x squared. And then this becomes 17x plus 30. We can actually do some factoring. This is x plus 6 times x minus 5. And then this thing over here is, this is 60, 12, 2x squared plus 12x plus 5x plus 30. 2x, x plus 6 plus 5x plus 6. Okay, x plus 6 times 2x plus 5. And then this is perfect, right? Because now our polynomial will be x plus 6 times x minus 5 times 2x plus 5. So therefore k is equal to 30. And we are done.